Welcome all. In last lecture, we have seen synchronous up counter, 2-bit synchronous up counter, 3-bit and 4-bit. Today, we are going to learn the design part of synchronous up counter, in which the steps are: first, we have to decide the number of flip-flops required to design the synchronous up counter. After that, we have to write the excitation table of flip-flop which we are using to design the counter. We have to draw the state diagram of the counter. After that, we have to write the excitation table of the counter which we are going to design using the excitation table of particular flip-flop which we are using. After that, from counter excitation table, we have to write the equations using K-map, and from those equations we are going to draw the logic diagram. Now we will see the first design, that is design of 3-bit synchronous up counter using T flip-flop. First we have to decide the number of flip-flops. Now here, as we are using 3-bit counter which goes through the 8 states, so it needs 3 flip-flops for its design. Now after that, we are going to have the excitation table of T flip-flop. We already studied how to write the excitation table of particular flip-flop from its truth table. Here they directly written the excitation table of T flip-flop. This column shows present state, this column shows next state, and this column shows T input of particular flip-flop. When present state is 0 and next state is 0, then T input should be 0. Present state is 0, next state is 1, then T input should be 1. Present state is 1, next state is 0, T input should be 1. When present state is 1, next state is also 1, then T input should be 0. So this excitation table we are going to use while constructing the excitation table of counter part. This is the state diagram of the 3-bit synchronous up counter, which starts from the initial state, that is 0, and ends with the final state, that is 7. This arrow indicates the direction of counting in ascending order, that is from 0, 1, 2, 3, 4, 5, 6 up to 7. After 7, the operation goes on repeating for the next negative edges or next clock pulses. After this, we are going to have the counter excitation table which includes the present state, next state, and flip-flop inputs. Now here we are having 3 flip-flops in a counter, so we have to consider 3 QC, QB, QA, that is 3 inputs of the flip-flop, 3 outputs of the flip-flop as a present state. The next state of the flip-flops are indicated as QC plus 1, QB plus 1, and QA plus 1, and TC, TB, TA are the T inputs of all the 3 flip-flops. Now here the present state is having 3 variables QC, QB, QA, therefore their possible combinations will be 8. We already know these 8 possible combinations, that is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So from this we have to write the next state of the counter at every clock pulses, after every clock pulses. So I can write the next state for this present state is 0, 0, 0. Its next state will be 0, 0, 1, means the count of this is 0 and its next count will be 1. Now here present state is 1, its next state will be 2 as it is up counter, so 2 can be written as 0 1 0. Now here next state is 2, present state is 2, its next state will be 3, which is written as 0 1 1. Now here present state is 3, its next state will be 4, which is written as 1 0 0. Now here present state is 4, its next state will be written as 5, which is denoted as 1 0 1. Here next present state is 5, its next state will be 6, which is written as 1 1 0. Now here present state is 6, its next state will be 7, which is denoted as 1 1 1. And the last one is present state is 1 1 1, which is the maximum count, so its next state will be 0, means after this the operation goes on repeating from the initial state. So using this present state and next state, we can write the t inputs of the flip-flop. So we have to decide the t inputs. Now if we will start with the QC and QC plus 1 column. So first the QC is 0, QC plus 1 is also 0. So we will observe this excitation table. When present state is 0, next state is 0, its t input is 0, so TC is written as 0 over here. Similarly, for next case, the QC is 0, QC plus 1 is 0, so its TC will be 0. QC is 0, QC plus 1 is 0, its TC will be 0. Now here for next case, QC is 0, QC plus 1 is 1. So now I will observe excitation table. Present state is 0, next state is 1. For that T input is 1, so TC will be 1. After that QC is 1, QC plus 1 is 1. Now I will observe the excitation table. When present state is 1, next state is 1, then T input is 0, so TC is written as 0. For next QC is 1, QC plus 1 is 1, therefore TC input is 0. For next QC is 1, QC plus is 1, therefore its TC input is 0. And for last QC is 1, QC plus 1 is 0. Now again I will observe the excitation table. For present state 1 and next state 0, the TC input is 1, therefore I will write TC as a 1 over here. Similarly, we can write the values of TB by comparing QB and QB plus 1, and we can write the values of TA by comparing QA and QA plus 1 with this excitation table. So after the completion of counter excitation table, we are going to find the value equation of flip-flop inputs, that is equation of TC, equation of TB and equation of TA using 3 variable K map. Now we will make the entries for TC. We know the sequence of entry from truth table to K map. The first 4 are 0 0 0 1, so I will write 0 0 0 1. This is the sequence to write into the K map. After that, next 4 are 0 0 0 1 0 0 0 1. This we already know how to write or how to make entries into the K map. Now here we can have a pair like this. So for this we can have the equation of TC as QB QA. After this we have to find the equation of TB. For that we have to make the entries of TB onto this K map. So here again the first 4 are 0 1 0 1, so I will write 0 1 0 1. Next 4 are also 0 1 0 1 0 1 0 1. Now here I can have a chord like this, and its equation will be QA. We know how to write the equation of particular pair, chord or octet. We already studied this while learning the K-map reduction techniques. After that, we will find the equation of TA. The first four are 1 1 1 1. Next four are also 1 1 1 1. So here we can have a octet. So for this we can write TA as a 1. Now we got the equation of TC, TB and TA. From that we can draw the logic diagram. We have to design 3-bit synchronous up counter, therefore 3 flip-flops are used. A common clock pulse is applied to all the flip-flops. After that, as per the equation, TA is 1, therefore this TA is connected to logic 1. TB is equal to QA, therefore this QA is connected to the TB input of flip-flop B, and TC is QB/QA, therefore this QB and QA output of flip-flop B and flip-flop A are connected to AND gate, and output of AND gate, that is QB/QA, is connected as input to the TC. So this is how we can design a 3-bit synchronous up counter using excitation table. After that we will design a mod 6 synchronous up counter using T flip-flop. So we already know how to calculate the number of flip-flops, as here mod 6 counter is having 6 states, therefore the value of n will be 6, which is less than or equal to, I will put value of m as a 1, which will give you 2, which is not true. After that we will write value of m as a 2, which will give 4, which is also not true, as 6 is not less than 4. After that I will write the value of m as a 3, which will give you 8, means here a 6 is less than 8, which is true. Therefore we are going to use 3 flip-flops to design this mod 6 synchronous up counter. Therefore we need 3 flip-flops. So after this we are going to use the T flip-flop. So we have to write the excitation of T flip-flop, which is written over here. After that we have to write the state diagram. As this is a mod 6 counter, it should have only 5 states, that is 0 1 2 3 4 5, 6 states starting from 0 to 5, and after 5 it should again gets resetted to initial state, that is 0. So by keeping in mind this state diagram, we have to write the counter excitation table. Again, as we are using 3 flip-flops, the present state will have 3 outputs, that is QC, QB, QA. Next state will be QC plus 1, QB plus 1, QA plus 1, and flip-flop inputs are TC, TB, TA. Now as there are 3 outputs, the possible combinations are 8, which are written over here from 0 0 0 to 1 1 1. For each state, present state, we have to write the next state. Again, the first state is 0, its next state will be 1, that is 0 0 1. Next state is 1, that is 0 0 1, present state. So its next state will be 2, which is written as 0 1 0. After that the present state is 2, its next state will be 3, which is written as 0 1 1. After that present state is 3, its next state will be 4, which is written as 100. After that present state is 4, its next state will be 5, which is written as 101. After this state 5, the counter has to go to the 000. Therefore for 5, that is 101, the next state is written as a 0 instead of 6, that is 000. For 6 present state, the next state should be 7, so we have to avoid that also. So for that also next state is 0, and for 7 the next state also 0, which is written as 000. So as our state diagram does not consist of state 6 and 7, so we are writing the next state for 5 as a 0, next state for 6 as a 0, next state for 7 as a 0. So here we have avoided the next state, that is 6 and 7. So this is how the excitation table is designed. From this again we have to write the values of TC, TB and TA by using this excitation table. For TC we have to compare this QC and QC plus 1. For TB we have to compare this QB and QB plus 1. For TA we have to compare this QA and QA plus 1. Only we have to take care that our excitation table in which a next state column is there, it should not consist of the next state after the 5. It means after the state 5, that is 101, the counter should goes to 0 and start with the original count, that is 0010101110101. After that again it should goes on repeating through the state 0 1 2 3 4 5 only. So from this counter excitation table we can have the equation of TC, TB and TA. So here first we will find the equation of TC. For that we have to make entries of TC, that is 0 0 0 1 0 0 0 1. After that TC is 0 1 1 0 1 1 1. Here we can have 3 pairs. This is 1, giving the equation as QB QA. After that we can have this pair giving the equation as QC QB. We already know how to write this. After that we can have this third pair which will give the equation as QC QA. We are going to add all these 3 terms to get TC. After that we will write the equation of TB. So the entries are 0 1 0 1 0 1 0 1. After that next entries are 0 0 1 1. So here we can have 2 pairs. This one which will give the equation as QC bar and QA, plus the next pair is this which will give the equation as QC QB. So after that we can have the equation of TA. We will enter the values of TA. First are 4 1 1. After that next 4 are 1 1 0 1 1 1 0 1. So in this we can have 4 chord. This is our first chord, which will give the equation as QC bar, plus we can have the second chord, which is over here, which will give the equation as QB bar, and the next chord is this one, which will give the equation as QA. So after having all the equation of TC, TB and TA, we can draw the logic diagram, which consists of 3 flip-flops A, B, C. A T flip-flop is used over here. A common clock pulse is applied to all the flip-flops. After that, as per equation, the TA is QC bar plus QB bar plus QA, which is formed using this OR gate. The TB equation is QC bar QA plus QC QB. So this will give you QC bar QA and this will give you QC QB. To add both this term, another OR gate is used, whose output is connected to TB. And after that, for TC, QB QA is formed with this AND gate, QC QA is formed with this AND gate, and QC QB is formed with this AND gate. And to add all these three terms, another OR gate is used, whose output is connected to the TC input of flip-flop C. So this is how we can design the Mod 6 synchronous up counter. After that, we will have the up-down synchronous counter. In up-down synchronous counter, all the flip-flops operate in toggle mode. So either T flip-flop or JK flip-flop is used. All the flip-flops receives a common clock pulse. Only Q or Q complemented output of previous flip-flop is connected as flip-flop input through the combinational circuit. So we know for synchronous up counter, a Q output of previous flip-flop is connected as the input of next flip-flop, and for the down counter, a complemented Q output of previous flip-flop is connected as input of the next flip-flop. The selection of Q or Q complement output of previous flip-flop controlled by the mode control input M. If M is 0, the counter acts as a up counter, and if M is 1, the counter acts as a down counter. So this is the diagram for 3-bit synchronous up down counter. It will act either as up counter or down counter depending on the value of M. When M is 0, this line will be 0 and M complemented line will be 1. So the 0 is given to this AND gate 3. Irrespective of QA complemented value, its output will always be 0. Therefore, this AND gate 4 will receive 0. Its output will be 0. So AND gate 3 and 4 will be disabled by this, and as M complement is 1, this AND gate receives 1, which will output as per value of QA. Therefore, we will get at its output QA. So QA and this 0 will give you QA. So QA is get connected to TB. And similarly, as here we get QA and this is QB, this QB QA gets connected to TC through this OR gate. So normal output of previous flip-flop gets connected to the T input of the next flip-flop. So this is the same as a normal up counter. So with M0, AND gate 1 and 2 are enabled and AND gate 3 and 4 are disabled, and circuits operates as a up counter. So with M is equal to 1, this line will become 1, this line will become 0. So this 0 is connected to AND gate 1 and AND gate 2, that is irrespective of QA, output of this AND gate will be 0, by which output of AND gate 2 will become 0. And with M1 which is connected to AND gate 3, so it will output as a QA. So this 0 and QA will give ORed with this, which will give QA and which is connected to TB, and this QA complement is given as input to this AND gate 4, and QB complement is there. So QA complement gets connected to this TC through this OR gate. Therefore in this we can observe that a complemented output of previous flip-flop is connected as T input to the next flip-flop by enabling AND gate 3 and 4 and disabling AND gate 1 and 2. Therefore these connections are normal as that of down counter. Therefore with M is equal to 1 the circuit works as a down counter. So this is the homework which we have to submit it to me on or before 31st December. In this we have to design a 3-bit synchronous up counter using JK flip-flop. We have designed it using T flip-flop in this lecture. After that you have to design a mod 10 mod 13 synchronous up counter, and you have to design a 3-bit synchronous up down counter. All these problems are solved in a TechMax. You can refer the TechMax to solve these problems. And this is the last one, is the you have to compare the synchronous and asynchronous counters. So you have to complete this homework and submit it to me on or before 31st December. If any query in solving these problems, you can ask me in the next lecture. Thank you.